model that we can also model them as not one continuous, for example, pyramid, let's say, but as some several different. And this is because during the formation, the tectonic plates just break, actually, and fall. Okay, so the other type is volcanic and cryvolcanic. Here we can see the tallest mountain in the solar system, the Olympus Mons on Mars. And here we can see also the Mauna Kea on Earth, the tallest volcanic mountain on Earth. And also we can model them as cones. This is something very important. They are made from basalt. The impact type, well, they are made from debris after an impact around the rim of the crater. And we can basically model them again as the tectonic mountains because of the large radius of the crater most of the times. Okay, so now models and criteria. Okay, so first of all we have the melting of the mountain bedrock. Well, when the mountain gets heavy enough, the pressure at the bedrock is high enough so that the bedrock melts, and this in turn makes the mountain less high. And we will investigate when that happens. So we can derive this formula where this is the density of the bedrock, the specific heat for melting, the density of the mountain, and the gravitational acceleration on the surface. Here we have for the model for tectonic impact the volume of the solid we are looking at, and in turn we get this formula. We'll see results in comparison in the end. Here we can see the same thing for volcanic and cryvolcanic. This time just the volume of the cone is 1/3 of this product and not 1/2. Okay, so the results, we can see the theoretical and in reality what's happening. You can see that they're a complete overestimate, and this is because there are other criteria. Now let's see what are they. Okay, so the next criterion is the yielding criterion. That means when the mountain couldn't supply its own weight, and that's when the rock itself breaks. And this happens when the stress or the shear stress is equal to the so-called yield strength, which we will denote by 1. Now let's apply dimensional analysis, because why not? And we find this relation where omega is a numerical factor which depends on the form, and we'll derive this thing. Okay, so let's suppose we have some form of a mountain, and now let's suppose that at some point when the stresses are large enough, the mountain breaks along this plane. This is just a model. Then we have some notation just for convenience, and this portion on top should be in equilibrium in order for not to fall. But at the point when the yielding criterion is met, it breaks. And in fact, it should support, the weight, and this is counteracted by the normal force and the shear force. By these considerations, we can apply some mathematical models, and we get this formula which connects the highest possible height with the density, the gravitational acceleration, the yielding stress, and the base, half the base of the mountain. This is made for tectonic. Also, we have one more criterion about the moment balance. If we look at this mode of fracture, we can see that there is an unbalanced moment, which should be balanced by the shear stress. And we get this other criterion, so we get this overall criterion, which for the Himalayas is 57 kilometers, though we have to, in fact, look at something more sophisticated, and I mean by that the model where the tectonic mountains are made up of smaller peaks. And by that, when the height is of the order of magnitude of the base, we get the 31 kilometer limit. Also, for volcanic, we get this criterion. It's exactly the same way obtained. And also, there's one more criterion, which is in fact connected to volcanic mountains. And that at some point, in order for the volcanic mountains to form, the lava from below the tectonic plates should go outside the volcano in order to harden there and make the volcano mountain. For this, the pressure here should be big enough in order to push the lava outside. And that means that we can apply this criteria and we get this, which in fact doesn't depend on the surface gravity, which is particularly interesting. Now for volcanic mountains, we get this from the considerations I explained before. And also, if we know the angle of repose of the basalt of the volcanic mountain, we can in fact transform this to this. So we have a test for model 2 which is more significant, statistically significant, and this is when we check what is the biggest, what is the critical size of asteroids when the flatness of the asteroids is no bigger than 10%, and when we apply the numbers we get in fact 270 kilometers, which is very near to the real number of 300 kilometers that is measured. So this is the numerical estimates. We can see the data there. Conclusion and final remarks. We analyze different things. We also see that they're complete overestimate because of the fact that we have a lot of outside factors like erosion, already present mechanical stresses and things like that. Also, most of the values are not accurate because we cannot measure them or calculate them theoretically directly.
Okay,
References.
Okay, we're out of time. Thank you. Thank you for the report. Clarifying question from the opponent, please.
Hi, my name is Lena, and today I'm from Bulgaria. The first question that I'd like to ask is, when the height increases, does the surface area increase, or actually stay static?
The surface area of what?
Of the mountain itself.
Of the base of the mountain?
Yes.
Or of the base of the mountain? Well, if it is
Does
volcanic,
it increase or decrease?
it depends.
What?
It depends.
On what?
For example, if you have volcanic mountains, it depends on the angle of repose. If the height rises, the surface area on the bottom also will rise because of the
Okay, so the next question is, in your theoretical models, you didn't include friction. So how does the friction actually affect the mountain, and in which way does it affect it?
It's not
like the friction between the layers of the mountain.
what I include is not in fact friction. It's the way the mountain, in fact, it's rock. It's solid, but it is in fact deformable to some extent, and just like elastic things, it's deformable to some extent, and then this is basically an elastic force. The shear stress is basically an elastic force.
Okay, so there must be different shapes of mountains, and from what I saw, you investigated one of them as a cone. And what other shapes do you consider mountains as?
Well, for the volcanic mountains, we consider them as cones because basically that's the most common form. But for example, tectonic mountains, they can be considered, as I said, as solids of constant cross-sectional area, constant form of the cross-section.
Okay, so what is the substance at the base of the mountain?
Well, for example, for tectonic, for mountains, it's most often basalt. But for the material which is the tectonic mountains are made out of is most common granite. But they are different types. It depends very much.
Is it the same for everything in the solar system, or does it differ?
No, that's why we can't make perfect predictions because we don't know the exact composition of the different materials that are on other planets.
Okay, one of the questions is, does the atmosphere humidity actually affect the maximum height of the mountain?
Well, yes.
And in which way?
Well, humidity affects because this creates more erosion. For example, on Earth, though atmospheric pressure doesn't exactly apply this much because the order of magnitude of atmospheric pressure and the pressures inside the mountain are so different that we can neglect the atmospheric pressure at all.
Okay, and the last question is the limitations of your theory. Does it only work for the planets, or does it go for the rest of the solar system as well and other things?
Well, if you
A
apply
short
this,
answer, please.
okay, for if you use the yielding criterion, you can apply it to everybody.
Okay, thank you very much.
I'm from Team Georgia, and today I'm going to be the opponent for the problem number 2, which is mountains. First of all, I'm going to say the problem statement, which is what are the tallest mountains in the solar system, and it asks us to propose and analyze the theoretical models that can allow predicting the maximum altitudes of mountains on various celestial bodies. This is the outline of the report. I think that the problem and the interpretation was good, as well as defining the process, the movement of the tectonic plates. I think the theory was average simply because all models were simple and basic, even though the mountain shapes actually differ and are more of complex shapes than just the simple ones that were in the theory. The analysis for me was not good enough, simply because there was no comparison between the theory and the experiment, which I would love to see in the experiment. In the presentation, the parameters were average because he only measured height, and the conclusion was average as well. Now I'm going to be talking about the strength and the weaknesses of the report. The strength is that the tectonic formation of the mountains were clearly explained, and he showed 3 different theoretical models. And the weaknesses was that the mountain height was only measured from the base, the formulas were not explained properly, and there had been no graph of the theory and the experiment, as well as for the calculations. He only used simple form, as well as the triangle had been used in the second theoretical model. And also I would like to talk about the fact that I asked him about the atmospheric humidity, and I would like to further investigate that topic in the discussion as well, simply because the answer that I got doesn't actually match the logic that I have, because I think that atmospheric humidity actually helps the mountain grow higher because of the less pressure. And now here are the discussion topics. What factors determine the maximum height of the mountain? Which theoretical for him is the best, and why does he consider it the best? As well as, does atmospheric humidity affect the maximum height in the area? As I said a few seconds ago, how friction between layers affects the stability of the mountain, and celestial bodies and their mountains, simply because he only showed his theoretical models on 3 things, which was Earth, Mars, and one of the asteroids. And I would like him to talk more about other planets and maybe more other celestial bodies. Thank you for your attention.
Okay. Thank you very much. With that, we can proceed to the discussion between the reporter and the opponent.
Okay, so the first is what factors determine the maximum height of the mountain? Because the factors that you had, I feel like there are a lot more factors that you could have actually thought about and talked about.
Well, there are a lot of factors, and in fact, what factors you choose to analyze depend on what is your model of analysis. And for example, factors which always depend are the surface acceleration, gravity acceleration. Also, we have the density of the rock, the yield strength. For example,
how does the pressure work? Like when the pressure is less, does the mountain grow taller? Does it not matter?
Pressure where?
The atmospheric pressure or the gravitation force, like the gravitation of the planets itself. Does it actually play a role in it?
Yes, of course. If you don't have gravity, there won't be any stress inside. Well, we have to look at the theoretical model in order to answer how much.
Okay, the next one is, for you, which theoretical model was the best and why?
Well, for me, I don't think that there is a best theoretical model. They all act at the same time. That's why I used those strange, those, yes, I know.
Okay, but before that, let's talk about the atmospheric humidity that you actually had a different answer to. So mine, and I'd like to talk about that.
Excuse me, can you repeat the question?
The question about atmospheric humidity.
Yeah, okay. Okay, so about the atmospheric humidity, well, the humidity can act on erosion, and erosion is one very big factor for for this how high mountains can grow. In fact, for example, erosion can in fact influence the yield strength because it creates different.
Does it help the mountain actually grow, or does it actually grow?
Well, I don't see a way where humidity would help to grow.
Okay. What about the friction between the layers?
What do you mean by friction between the layers?
Between the layers of the mountain,
like an actual friction, or what I discussed?
The friction, actual friction.
Well, the friction actually.
Do you think it will give it a better outcome in a way, or is it gonna do only bad things? Because
well, for the theoretical model, it's definitely okay to consider friction because it's important. But you have friction when you have two different. You have bodies which are not part of the same body. Here you have a mountain that is basically made of almost one whole rock.
Okay, so the next question is, from what point did you actually measure the height?
I measured it only from the base.
And why did you measure it
yes,
from the base?
But in order for that, so if you have a mountain that's, for example, something like that. It's a very simplified model, but it will do. So we measure the height between this point and the place where the terrain, like the horizon, basically. And the reason for that is because it's completely for the reasons of the yield strength models. Because in order to calculate the strength, you need to see where those shear stresses are present. And when you have flat surface, you don't have shear stresses. You have just hydrostatic pressure.
And what I want to talk about is when I asked about the area actually increasing or decreasing, you told me that it depends. How can a mountain's area, the base area, actually decrease of a mountain? Because that would actually make the mountain.
Yes. Okay. So for the growing the mountain, like for the time evolution, you can't actually decrease the surface if this is what you mean, the area. Though,
when I asked the question, you said that it depended on the mountain
it depends
itself.
on the. Well, I didn't understand if you're asking for the time evolution of the growing, but if you're asking for the time evolution of the growing, it may grow always.
Okay, thank you very much for the discussion. Clarifying questions from the reviewer, please.
Alright, so first for the opponent, you said there was a best model, so you should have a different model, so what other model would you propose? So do you have an idea of a different model?
For me, I feel like every single model is going to have a fault in a way, simply because mountains can vary so much in the shape, and it's never going to be one shape, and it's also going to change in the shape. So I don't think that there's going to be a theoretical model that is ever going to be perfect for the mountains.
Okay. And the reporter, could you please define lava? Lava.
Basically, almost liquid rock. It's not completely liquid. It's just a state of matter that is with high viscosity.
In the mountain. So lava in the mountain. Can it be a
well, the lava in the mountain, like if you have a volcano, the lava in the mountain, okay. But lava in a normal mountain, there are a lot of mountains that have lava inside them.
Okay, where is the lava in the mountain? So
in a volcano?
Yeah.
Well, it's basically inside everywhere. Not everywhere. There are caves, so-called, where the lava is located.
Thank you. So why did you put density in the equation?
Excuse me?
Why did you have density in the equation? What does that do?
Well, the density is not a very important parameter. It's like if it's not the same if we use, for example, cotton and rock. They are completely different weight, and their weight will be very diverse. It will be very different.
Okay.
Like
And your
this.
model, is that for one material? What's the mountain?
Short answer, please.
Rock.
Okay.
Okay, thank you for the questions. Now you have your preparation time running. Thank you.